Well, we're on this screen. It's section 3.4. We're having some technical problems, but I think I figured out the issue was a full hard drive with just too many videos stored there and no free space, or headroom sometimes they call it, for the computer to operate. And then it would just hang, and I would look over at my monitor and it would say 36 seconds, and then it would stop moving. So that better not happen now. So here's the slide I was working on. I'd finished it. It was a beautiful thing, but now I'm going to have to go through it again. Here we go. Section 3.4, measures of position and determining outliers. So this particular slide is just going to cover z-scores. But later on the future slides, the rest of this section covers percentiles, percent of values at or below a given value in a population, quartiles, approximate 25th and 75th percentile values, interquartile range, the distance between the quartiles. We call the big quartile Q3 and the small quartile Q1. So the 75% of the values are less than the upper quartile and 25% of the values are less than the lower quartile. The interquartile range, the IQR, is Q3 minus Q1. It's the distance between the quartiles. We'll be computing that, and then we'll be using the 1.5 IQR rule. It uses IQR times 1.5, and the quartiles, these actual numbers you'll come up with, and to give a range outside of which we would call values considered to be outliers. Okay, got that under control. Up here is the definition of the z-scores. It's the number of standard deviations away from the mean. The way you compute it is by taking a particular value you might be interested in. So these are about values, percentiles and z-scores. You need a value to proceed. So we need a value, we'll call it x. We have the population mean, we have the population standard deviation. So say the population mean was 100 and x was 120. The top would be 20. And if sigma was 10, then 20 divided by 10 would be 2. That would say x is 2 standard deviations, 2 times 10, away from mu, above mu. So this is just converting everything into standard deviations. Positive ones is standard deviations above the mean, and negative scores are standard deviations below the mean. And then if you've got the population mean as standard deviation, that's what you really should use, but sometimes you don't have it. We use the sample mean as standard deviation instead. We can still compute what's called the z-score. Less often used and less often called z-scores. Ordinarily, z-scores have population mean and standard deviation, but just as well, sample mean and standard deviation. Z-scores can be used to compare positions of individuals in different populations because it's sort of an absolute measurement in terms of standard deviations away from the mean. So if you have different groups and you have different objects in each of those groups and you compare how many standard deviations away from the mean they are, you can compare their relative position to the mean in the various, the different populations can compare the position of the values relative to the mean, and that way you can judge them against each other. So for example, you might have an SAT score and a SAT score, and you might wonder what they correspond to. Are they about the same, or are you doing better on the SAT than the ACT? You could do that by computing z-scores for the values that tell you how many standard deviations away from the mean the SAT score was and the ACT score was. And then that could compare those. They should be pretty close to the same number, but you can see which one was higher or lower relative to the two peers. Our example is going to be 5K pace data based on age and gender, and we'll compare some 5K paces for men and women of different ages. And we have over here all the z-score calculations. And then we'll see who's better relative to their peers. That's the idea. So in this box is 5K pace data, made up data. Age 20, for all the 5K runners, the mean is 9 minutes and 33 seconds per mile. And the sigma for that is 1 minute and 37 seconds per mile. For women, 11:46 minutes per mile, 11 minutes 46 seconds. Sigma is 1 minute 42 seconds, etc. So here's age 50, a little bit slower, so these numbers are bigger. 10 minutes 54 seconds, 13 minutes 22 seconds, 1 minute 58 seconds, 2 minutes 10 seconds. So that's made up data, so don't take offense if your running speed is faster or slower. I bet you these sigmas are maybe a tiny bit too small, but whatever. Here are the people in question. They're also fake people based on the fake data. I like that. 20-year-old man runs 8:45 pace. 20-year-old woman runs a 10:52 pace. 50-year-old man runs a 9:20 pace. A 50-year-old woman runs a 12:25 pace. So we're going to compute the z-scores. The z-scores look like value minus mean over standard deviation. So for 8:45, convert that to decimal minutes. It's 8.75. So you take 45 divided by 60, and it gives 0.75. So 8 plus 45 divided by 60, 875. And then the mean is 933. So 933 becomes 9 plus 33 over 60. That's 955. So there's value minus mean. And then we take the standard deviation, 1.37, and 37 seconds divided by 60 is 0.617 minutes. So we get 1.617 minutes for sigma. So we do the value minus mean over standard deviation, converting the seconds into decimal minutes for all these people. So like 920, 20 divided by 60 is 1/3, so you get 9.33. And then the mean for the 50-year-old man was 10:54. 54 seconds comes out to 0.9 minutes, so 10.9 minutes. And here's sigma is 1 minute 58 seconds. That's 1.97 minutes. Okay. So we do also, it says, beware of minutes and seconds. Those aren't decimals. And then over here I've got all the z-scores. Smallest is fastest, because a small number for your time per mile corresponds to a fast runner. So being below the mean and the minute per mile time means you're fast. Being above the mean and your minute per mile time means you're slow. So smallest is fastest relative to peers. So all these people are running faster than the mean. Running faster than the mean means that this number is smaller than that number, so you get negative z-scores. They're all negative. Smallest is fastest means they want to pick the most negative number possible for the fastest among the group. So fastest relative to peers is the 50-year-old man whose z-score is minus 0.797 because it's smaller than all of these. Among the 20-year-olds, the woman was fastest relative to peers because that's more negative, so it's a larger negative number. So smaller is faster. So that's the smallest one in the 20-year-olds. So we made it through this slide without crashing my computer. And I think I've probably solved the problem because I don't know if I told this to you at the beginning of the slide, but the hard drive was basically full. And as it's trying to save the video as we're making it, it would get stuck. And now I cleaned out the hard drive. It's plenty of space. We should be fine for a while until it runs into that same problem again, which, you know, these videos take up a lot of space. So I've got to keep my eye on the prize, or pick a thing, go into the computer once in a while, and see how much free space is available on the hard drive, and make sure that it doesn't run out. Really, it makes it kind of angry. I'll see you in a minute. I'm shutting this one off.